Okay. That hit record, yes I did. So 3.2 was conditional probability in the multiplication rule. We were able to kind of define conditional probability. Conditional probability means like there are conditions, right? So just what it is that you're computing. The probability of an event given that another event has already occurred. That's not a bracket. That's actually supposed to be a parenthesis. The way we denote it is like it's the probability of B given A. And so it's right, the probability of B given A. We did an example of having two cards being selected. It said in sequence from a standard deck of cards. And it wanted us to find the probability that the second card was a queen, given that the first card that we picked was a king. And it's really good if it tells you that the card is replaced or isn't replaced, because that's what's going to help you differentiate between maybe the type of probability it is and the numbers that you're working with. So when it said given that the first was a king, I like the way that it followed the same verbiage that it did here when it talked about how this is denoted, because it said given A. So it said given that the first is a king, that told me that my A was a king. I know that 51 cards would remain because it told me that the king was not replaced. And then the other event that occurred, or what we're calculating if it will occur, is if the queen is selected next. And there's 4 total queens. So we do the probability of B given A. We have the probability of our B, which is the second card being a queen. And it's given that our first card is a king. There are 4 queens, and it would be out of 51 total cards because the king was not put back. And then whenever you use your calculator, we ended up getting that it was a 0.078% chance. Okay. And then this is just us doing it in class. The pages are doubled up. Okay, and then we had this problem right here. So it says 2,276 social media users are asked if they've ever been offended by something online. Find the probability that the user is male, given that the user was offended online. Okay, so if you look at the little table, we have female. This has nothing to do with female, so I'm not going to have anything to do with this row. This is our males, and it does want me to figure out the probability that the user is male. So I know I'm going to have something to do with here, with this row, right? Then it says given that they were offended. So that's what tells me I'm looking here. So this is male and offended, and then your denominator is going to be the total in that same column. So the user is male was 532, and then the user being offended, the total is coming from all offended. Okay, I know that one kind of seemed confusing the other day. Maybe it was just me that got confused. So the probability of B given A, so the probability that the user is a male, given that he was offended online, is 532 over 1151. So it ended up being a 0.462. That was the probability. And that is the decimal. That's how you'll enter it into your homework. And then this was us just doing it in class. This is where we're starting now. We're going to talk about independent and dependent events. And then I think I have 2 examples, and then we'll do the multiplication rule. Sorry for my voice. I can only imagine how bad this sounds on the video. Okay, independent and dependent events. They are kind of the same way that they sound, right? Independent and dependent events. Okay, I'm going to open my brand new pens. For for independent, I've got a couple of little bullets underneath it that I need to scribe. Sorry, y'all. I know I love purple. Let's see how this writes. Okay, so independent. So for an event to be independent, what we have here is the occurrence of one does not affect the occurrence of another. So one event happening, no matter what event it is, it doesn't have the ability to affect the next event happening. That's what makes them independent. So one occurrence of one does not affect the occurrence of another. And then this is what we do whenever we are talking about independent events. Here, let me just write it because it's just easier to write than it is to say, because it's just like a little formula. If we have the probability of B given A, and these are independent events, meaning that this happening doesn't affect this happening, the only thing we actually have to do is just compute the probability of B. And it's because it's not affected by A. So given that A occurs, it didn't affect B, so all I really need to know is just the probability of B. Okay, now let's say that our B and our A were flipped, right? Instead of B given A, say we were given the probability of A given B, all we need to do is just figure out the probability of A. So whatever the first one is, if they're independent, so we just have this, or there's this setup with probability of A given B. If these are independent, if one is, and I think our example, y'all, is going to be like a coin and a dice. Or like, it doesn't matter, whatever I flip the coin, whatever I land on did not affect what my dice is going to be landing on. And so we would only need the probability of the first, whatever one's the first one. And then they go ahead and they say this, I guess just for continuity. Events that are not independent are dependent. So that would be like you're rolling the dice 2 times. Or that might, I probably wouldn't write that. Just go out with my wording's exactly right. But Belinda, can I give you this? Mm-hmm. Yeah? I'm just sitting there thinking, I'm like, when I start writing, I don't want to turn around and lose my place. Thank you so much. For now, just kind of leave it that they're not independent, they're dependent. When we do the example, that'll be better, because I get ahead of myself, I'll say something that's not completely correct. I don't want to do that. Oh, I was right. Okay, that's what I make sure. Okay. Actually, I was backwards. Let's do this example. Okay. So say we're tossing coin and getting a heads, and then in parentheses they go ahead and they call this, that's our A. Then rolling a 6-sided, they call it a die because it's just one, and getting a 6. They call that our event B. And I kind of just like rewrote what they wrote. So I was like, okay, so we have, I mean, you could just write heads if you wanted to, but you know, getting heads is our A, rolling 6. That was our B. A paper sideways, the camera sideways, everything sideways. I didn't win. Okay, So if I roll, or if I flip, this coin first, and then I roll the die, does it make sense that they didn't affect each other? They're two different things that are happening, and they're not happening even with the same thing. One's a coin, one's a dice. And so this is why it is a independent event. Tossing a coin and getting a heads, then rolling a 6-sided die and getting a 6. So what we have here is the probability of, it says B given A, would be equal to, so this is what they're telling me to compute. This is what we know, and then they're like, okay, go ahead and compute the probability of B given A. Go ahead and compute the probability of rolling a 6-sided die given that you've gotten a heads, right? These are independent. Because they're independent, all we have to do is just figure out what the probability of B is. Because they have nothing to do with each other, they're independent. The probability of B. So, remember, it's like favorable, or like what are you looking for, or what is the number of outcomes in this event over the total. How many times could you get a 6 when you roll a 6-sided die? It's just one time. That's your one outcome that exists. So it's your total number of outcomes over like your sample space, basically, right? And there are 6 different rolls that could occur, but there's only one time that you're going to get a 6. Okay, and the reason why I can do this is because the coin and the die have nothing to do with each other, so they're independent. Now, if you put that into your calculator, I don't know if it didn't show it to me as a decimal or if it was just 1/6. Sometimes it will tell you it wants a simplified fraction, and if it does, you just use the fraction. But let's say that, we want to just also see our percent. Belinda, what did you get? Bless you, bless you, bless you. 16666, so 167. Gesundheit. Like it would tell you where to round it to. I'm gonna go grab my calculator. Because that's what I thought it was, but I didn't want to be wrong. Oh my gosh, there's so much stuff in here, though. I've got like all of Dominique's calculators in there. Okay, very good. Does that make sense, though, as far as it being independent? Okay, because like that does change the actual math that you do. So just make sure you understand that. Okay, let's do the second example. And this is really just kind of writing a couple of sentences, but there was a handful of these on the homework, so that's why I wanted to make sure that we included them. For the second example, it just says which is independent and which is dependent. I'm just going to write independent or dependent. We have A. Speeding and getting a ticket. Independent means the occurrence of one thing happening cannot, or like does not affect the other occurrence. But if you speed, it will affect your getting a ticket, basically. And so you would say that this is dependent. This is not independent. Those actually could result in the other. It's like taking driver's education courses and getting your license. Those affected each other, right? This is where I said the wrong word a minute ago. I said a second ago about rolling the dice multiple times, and I actually called it dependent. let's say we did roll a die 3 times. What I get on the first roll does not affect what I get on the second roll. They all have an equal chance every single time, right? So that's what makes it independent. I did accidentally, about a page ago, said dependent, but it's independent. I think there's one that says something like, dressing nice and combing your hair. Like, you might get a job. It's like, oh, yeah, I could see that happening. You know, like those would actually be dependent on each other, right? Because if you don't do the first one, you probably could have kept the job. That makes sense, y'all? Okay. Hey, good morning. You need one of those. One of each. Good, how are you? Okay. I'm okay. Actually, I feel a lot better. Like, so much better. Like, I'm feeling like myself again. Okay. Y'all, if you're okay with that, I'm going to switch pages just because I know that I've got, like, the definition. I'd like to fit an example on it, too, in case I print these up for someone or someone reaches out and say that they need them. Keep it all together. Okay, the multiplication rule. So we have the multiplication rule, and for the probability of A and B, so for the probability of A and B, I got a bullet. And it says 2 events, A and B, so 2 events occurring in sequence and dependent on each other. What we would do is we would take the probability of, and they just go ahead and they write out A and B. So like in math, if we're doing like this and that, we would be multiplying together. That's why it's going to be called the multiplication rule. And so the way that we would figure this out is we would take the probability of our event A and then we multiply it to the probability of B given A. So the probability of B given A, that was all the previous section we did. Now if we see the word and, we would take the probability of the first one, multiply it to the probability of, and you kind of flip the position it's in here, B times, or B given A. And y'all remember that formula I gave y'all? Like this is on here. Okay, like if you see it, you'll have the formula in front of you. So this is like for a dependent event, right? Let's say for independent events. The rule can be simplified to so instead of having the probability of the first event multiplied to this, which is the conditional, what you would do is you just take the probability of your first event and you multiply it to the probability of your second event. And I could do that because if they're independent, then one happening doesn't affect the other. All I have to do is multiply each of their probabilities together. Now, if they're dependent and they do rely on each other, that's when I need to use the conditional probability that we learned in the last class. Okay. And there is a note that just says this could be extended for any number of events. So if you have A, B, C, D, E events, there's 2 problems at the end of the homework that we'll end up seeing like more things happening, but I don't think that we need that note for this. Let's do an example. So you can actually see what all of these words mean, like put into action. Okay, so I actually have 3 examples that we're going to do. For the first one, it is a lot of writing. I am really good today. 2 cards are selected. Comma, not replaced. From a standard deck. They just say that so that you know that there's 52 cards in it. Remember, I gave you all that pass out that has the picture, so you've got that data, like that information. Okay, so what we're going to do is we're going to find probability of selecting a king and then a queen, okay. So what we have here, the first card is not replaced. They told us that, right? So this is actually going to be dependent events. Okay, as far as the math is concerned, when a card is not placed back into the deck, it changes the probability of the next one. It actually does affect the next one. So first card is not replaced, so dependent. I kind of ran out of room there a little bit. But that means that we're going to do this first example. And if y'all remember, we did this example in the previous section when we did the conditional probability, right? So it kind of like, they're kind of trying to keep the same type of example there, so hopefully you know something does look familiar for you. So what do we need to figure out? We need to figure out probability of selecting a king and then selecting a queen. Dependent, right? They rely on each other. Not really rely on each other. Let me say it like that way. One is affected by the other. So that's this formula right here. Okay, that's this one right here. Because they occur in sequence and they rely on each other. So we take the probability of A, which is, do you see how A is our K? It's the first thing. Okay, so what I'm going to do is the probability of K. And then I'm going to multiply to that the probability of B given A. Well, in this order, what we see is that our queen is our B, right? And then our king is our A. So it's going to be the probability of getting a queen, queen given king. And that's what we did in 3.1 now. This is what we've seen already, okay? So I'm just going to kind of go down like this, just so I can write them underneath it, really see what's going on here. How many kings are in a deck of cards? And how many cards are in a deck of cards? 52. So the probability of a king, remember, probability, y'all. It's like, I've always said, like, what are they talking about? What are you looking for over total? Right? So what are we talking about? We're talking about kings. How many kings are there? There's 4 kings. Over total, 52. So we have 4 over 52. That's the probability of selecting a king. And that's why I keep saying, like, it being replaced and it not being replaced is a big deal. Because my denominator now, whenever I do, like, I move on, is going to change if it's not replaced. There's no longer 52 cards. If that king is not put back in the deck, there's now 51 cards, right? How many queens are there? There's also 4 queens. So I'm going to multiply that. And remember, we did this, so I'm not trying to explain the conditional probability again. But we would be looking at the total number of outcomes and then like the total, like the sample space. The total number of outcomes is the fact that we have 4 queens in the deck and there are 51 cards that remain, okay? It not being replaced did affect this probability, which is why we needed to do the conditional. And so, I just had the answer somewhere. If you put it in your calculator, I'll go and show you how I would probably do it. What was I doing? Oh, sorry. I was grading exams yesterday. I was like, why do I got all those numbers? Okay, so I would probably go like math and then go to the left to get that fraction n over d and do 4 over 52. And then you have to scoot over to get out of your denominator and be blinking back in line with your fraction. And I would do the multiplication symbol. And then I'm going to go math left, enter again to just kind of grab that fraction. If you do parentheses to like separate this or that, like it could mess up. So it's kind of a little bit easier this way in my mind. I've got 4 over 51. Now using my calculator, it's already going to go ahead and get it into the smallest reduced forms. But the answer that they want, because we're talking about probability, is going to be like in a decimal form, right? So what you would want to do is you could hit math. And then that second one where it has like a sideways triangle and it says DEC, it's like converted into a decimal. And so I get 0 point, and it has usually been telling you to round to like 3 decimal places. So it'd be 0.006. Like that's a really small, right? Very unlikely probability that you're going to have a deck of cards select a king and the next being selecting a queen, right? Remember we talked about that right there as well. What I did is I just wrote down what they were. I used my calculator and I got 0.006. Did it make sense how I said that was a very unlikely probability? Remember, because it's really, really, really close to 0. It's not close to 1. Okay? Does that make sense, y'all? Yeah, and it's rounded, so you'd actually probably use like the squiggly equal sign. You might see that on the homework. Okay, we got 2 more examples for this. Okay. Second example, tossing a heads and rolling a 6. Didn't we just do that? I guess I use the same examples over and over again. Let me see what we did. Oh, that was the conditional. The conditional was that, but it was the same thing, a heads and a 6. So, same words, which kind of make it confusing in my mind, but this is like a different example, believe it or not. Okay, yes. Yeah, no, you're fine. Tossing a head and taking, what? I was going to say taking a 6. Tossing a heads and rolling a 6. And we're looking at a similar example that we've already done, but we're looking at it in the eyes of like, is it independent or dependent? And we're going to use the multiplication rule. Okay, and we learned this whenever we saw this example a minute ago. But if you think about the heads being a coin and then the 6 coming from the dice, like they are independent of each other. No matter what I get when I throw that coin up in the air is not going to affect what that dice rolls on. They are completely independent. So I just kind of did a little asterisk and I said it's like independent. And then I went ahead and solved it the way it told me to. And I can't spell. Independent. Okay, so we have the probability of a heads and a 6. I just looked at both of them and I thought about, does my coin affect my die? And it doesn't, so independent. I look back at the multiplication rule, I look where it says independent, and it says that when they're appendant and they're not affected by each other, we don't have to do the probability of the first one and then do the conditional afterwards. All we need is the probability of the first one, multiply it to the probability of the second one. And so I would be finding the probability of heads, and I would multiply it to the probability of rolling a 6. So probability, right? Favorable over total. Or what are you talking about? What are you looking for? How many outcomes over total? How many outcomes are there, right, for our denominator, for the probability of getting a head? So we have tails and we have heads. That's my sample space. That's all I could roll, is a total of 2 different things. Now, the probability of getting a heads, I just want that one outcome, right? There's only one outcome in this event, in this probability occurring. And so I would have 1/2. And I'd be multiplying it to the probability of rolling a 6, which is there's 1 6 out of the 6 rolls that could happen. And then you would just multiply these together in your calculator. You would get 0.083. Okay, I like this example. I don't know why, but I just do. This third one. So, this is the last one for 3.3, okay? So, selecting a face card. Then F5. I probably could have actually just written up the word 5. I didn't do the 6. I guess it's okay. Not replaced. And so, you have that pass out that I gave you that I told y'all could use during the test. First, let me go ahead and just kind of look at this. So I'm looking for the probability of face card and then a 5. Does the card that's first being selected not being replaced affect the occurrence of the other one? Right? Remember, like if I have 52 cards and I pick up a card, right, and I don't put it back, the fact that my sample space was just affected and it went from 52 to 51, these are dependent. Not replaced means dependent. Okay? Cards not being replaced means it's dependent. If every time I pick it up and I put it back, they're independent. It's the same 52 full deck of cards each time, so they're just completely independent of each other. If I take it and I mess with that deck of cards and I don't put it back, the next one is affected by it. And then say I select another card, and then another one, and another one. Okay? So what we're going to do, because these are independent, I hate the way they're so close together and I mess up, because these are dependent events, is I need to figure out what the probability of a face card is, and, which is multiplication, the probability of a 5 given a face card. The probability of selecting a 5 given that the first card that we selected was a face card. So if you look at what I gave y'all, this is a deck of cards. Okay? So half of them are black cards, the other half of them are red cards. Okay? We have a total of 4 aces, 4 twos, 4 threes, 4 fours. So that's, it's like a pattern kind of going on here. We have 1, 2, 3, 4 different suits right here. Those are your face cards. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. In the probability of selecting a face card, there are 12 outcomes that are favorable. There's 12 outcomes that I'm looking for, that I want, right? And it's out of how many cards total? 52, because it's the first one that I'm selecting. The deck's brand new, right? Nothing's been taken out of it. So the probability of a face card is there are 12 face cards out of 52 that I'm selecting from. And then remember with the conditional, whenever we have 5 given a face, what we do is we're going to look at this first thing that's going to occur, which is a 5. That's my numerator. It's like how many 5s are there? How many outcomes would I result in a 5? There's 4 5s, and I just go to the 5s and I'd count 1, 2, 3, 4. There's 4 5s. Now because this is conditional, because it was dependent, what matters here with the face cards, given that the first one was a face card, what they mean by that is it wasn't replaced. So now my sample space is no longer 52. Given that the first one was a face card and it was not put back into the deck, now my denominator is not 52, it's 51. You don't do 4 divided by 12 or anything like that. Okay, what it's really doing is it's kind of like, hey, tell me the probability of this happened, but there was something else that happened before it and it's affected this. And what it means by that is that sample space is now 1 less. Okay? And if you use your calculator, you're going to get 0.018. If y'all notice, these have been like really low probabilities too, because like that would be insane to like, you know, specifically get these cards. Okay, does that make sense, y'all? There's a lot of words, okay, but the multiplication rule uses what we learned at the beginning of this, which was the conditional probability, okay? And then there is a big difference between independent and dependent, because it's going to change the way that you can compute it. It's actually easier, or it should be easier, when they're independent, because nothing's being affected as you do the math. You don't have to sit there and question 52. Okay. Let me think of this one. I'm going to do this one free of charge. So it's pretty much the same type of wording. Just going to change a couple of things so that we could do an example where it's independent, and then you can kind of see what I'm saying as far as like, oh hey, they weren't affected, right? So selecting a queen and then a face card, assume cards are replaced. So I've got a whole sample space of 52 cards. What's the probability of me selecting blank? Okay, and then I put that card back. So do you see how it's like I kind of started fresh? Now the probability of me selecting another thing was not affected by the first thing. Okay, and so what I would have here is the probability of a queen and then a face card. Okay, these do not affect each other, so they are independent. Events. And that's because I put that card back, right? So brand new, fresh probability each time. Well, they told me that if I have my and, which is multiplication, and they are independent. Oh, where'd my notes go? There we go. For independent, multiplication and probability of A times probability of B. I don't have to do the conditional. I don't have to sit there and think about anything that was affected. I just literally do the probability of A and then the probability of B. So the probability of A, like that's that first thing. So I think about the probability of selecting a queen, and then I'm going to do the probability of selecting a face card. So if you look at your, deck of cards there, there's how many queens? There's 4 queens out of my whole sample space. Hasn't been touched. It is all 52 cards. And then I place it back into the deck, which is what makes this independent. And now I say to myself, what's the probability of just getting a face card? Well, there's 12 of them. Out of how many? I've got all 52 cards in my hand right now that I'm selecting from. And then you just multiply these across. Excuse me. And I love this calculator because I could just go up and I could highlight the previous one that had 2 fractions, right? And then just move my cursor over on this denominator. I'm going to change that to a 2. And then right here, I'm going to type 12. First one I already had it, and that's hit enter. And then I will do math option 2 to convert it to a decimal. And I get 0. If we were to round this, y'all, to 3 decimal places, 1, 2, 3. To my right is a 7, which means it's going to become an 8. That fourth 7 affected that third 7 by me needing to round it up. Okay. That makes sense, y'all? Yes, no, maybe so. So that ends 3.2. We click on the screen and then touch the red. I really just wanted you to